So we can start. I've got a little bit more material from lecture 2 I want to go over. This is related to purifications and Schmidt decomposition, so I think that'll be just a recap or a review. And then we're going to apply this to another subject in cryptography called bit commitment. Okay, so yeah, starting with Schmidt decompositions. If I have some pure quantum state, let's call it psi, in a bipartite Hilbert space on AB, then it turns out that there's always a way to express this in the following form, right? So I just have one index I, and it runs over a set of vectors that live in the A Hilbert space and another set that live in the B Hilbert space, and then there's some coefficient lambda I, taking the square root for each I. And you should contrast this with sort of the most naive expression that I would have for the state, which might look like this, right? So if I just had, if I started with the totally general state and I just thought of any basis for the A Hilbert space and whatever other basis for the B Hilbert space, I would have a state in this form where this index would have two, or this tensor would have two indices, right? But the point of the Schmidt decomposition is that there's some special basis of A and some special basis of B, such that I simplify and I just have one index here. Okay. One thing that's nice about this form is that it's simply related to the density matrix on A and B, in particular when I diagonalize those density matrices. So you can see that if I started with this state and I traced out B, because these vectors are orthonormal, I will get something diagonal here. And I take a ket and a bra, so I get like 2 square root lambdas, so I end up with the lambda. Okay, so I end up with this. So it's like this basis, the Schmidt basis for A is also the basis that diagonalizes rho A, right? And then similarly for B, if I wrote down the B density matrix, it would look basically the same. Okay, so some language. These are the Schmidt vectors, and these are the Schmidt coefficients. Okay. Another sort of piece of language. So if we have some density matrix on A and a state on AB, and we have that the trace over B of psi psi AB is rho A. We say that psi AB purifies rho A, right? Good. And then there's an important statement about how different purifications of the same density matrix are related to one another. So there's a theorem. I think you saw this in quantum theory, so I'm not going to prove it, but I'm going to write it down. So all purifications of one density matrix are related by isometries on the purifying system, on purifying systems. Okay, so what does this mean? It means, let's say that psi, AB, and phi okay, so this is sort of IE, explained another way. Psi and phi both purify. Oh, actually, let me be a little bit more general. So psi AB purifies rho A, and then phi like AC also purifies rho A, right? So B and C could be different Hilbert spaces. One of them could be bigger than the other. Then what we have is that there's always going to exist. Okay, let me say that. Let me say that the B Hilbert space without loss of generality is not bigger than the C Hilbert space. Then there exists isometry from the smaller space into the bigger one, from B to C, such that phi AC is equal to VB AC psi AB. Okay. So an isometry, remember, is a map. Maybe write it like this. Okay, so it's a map from a smaller, it can be a map from a smaller to a larger space, but it has the property that when I take the adjoint and I go back from the larger space to the smaller one, I just get the identity, right? So it's sort of like a unitary, but the Hilbert spaces can be different size. I know, have people seen that before, like in linear algebra? Or sometimes this is weird.
But should there be only one dagger?
Yes, there should only be one dagger. Okay. Okay, so this is fairly simple to prove. Actually, the simplest proof uses the Schmidt decomposition, and you kind of write down that isometry V in terms of the Schmidt vectors on the B and C Hilbert spaces. Okay, so good. Something that might be a little bit new is it's useful to be able to construct one particular purification. So they're all related to each other, but if we want to just write down one, there's one called the canonical purification. Okay, and the way it works is if I start with some density matrix sigma A, I just choose the state square root sigma A, acting on psi plus A bar. Okay, and maybe I can also call this like psi sub sigma. It's a purification of sigma. Okay, so what does this mean? Sigma is a positive positive matrix, so I can make sense of the square root, right? And what I'm doing is I'm acting with that operator formed from the square root of the density matrix on one end of the maximally entangled state. So that's my psi plus is the maximally entangled state. And we can check that this is a purification. So to do that, let's say, okay, so sigma A, this is a Hermitian matrix. I can diagonalize it. It's going to look like this. Okay. So then square root sigma A, or one root of square root of sigma A is just this one. Right? If I multiply this by itself, I'm obviously going to get this. And then if I act that, so if I act that on psi plus A bar, what is that? Well, square root sigma A sorry, this, I feel like I need to make some notation here. So let me call, when I put a twiddle on top of psi plus, that's the unnormalized maximally entangled state. Okay, it's not really a state, it's just this. Well, it's this, right? But I don't put any 1 over root d. Yeah. Okay, so this is totally guy. Yeah. Okay, and then I just multiply this out, so I get sum over I, sum over j, square root lambda j, psi j, I. Oh, sorry. Okay, so the maximally entangled state, it doesn't really matter which basis I write it in. It's sort of like how the identity matrix is like all ones on the diagonal, no matter which basis I think about. So I can actually, just for simplicity here, choose the basis I write this sum in to be the basis that diagonalizes sigma, right? It's going to make my life easier. So this is sigma I. Okay, and then this is some orthonormal basis, so that's delta ji. And so what am I getting? One of the sums is going to go away. I get a sum over I square root lambda I, psi I. Okay, and this is on like a bar. Okay, and then you can check that if you were to trace out the a bar Hilbert space, that you'll get back the density matrix on sigma. Right. Okay, so that's one purification. We're going to call it the canonical one. It'll come up later. And then all the other ones are basically this one with some isometric map acting on a bar. Okay. Questions about the recap of purifications? Okay. Okay, so I want to discuss a QI application of this, which is a subject in cryptography called bit commitment. Okay, so the setting here is, as usual, we have Alice and Bob. Okay, and what they want to do is sort of mimic the following functionality. So this is sort of a metaphor for what we want to happen. Okay, so Alice is going to decide on some bit, which could be 0 or 1, and she's going to put it into a safe. Okay, so that, I don't know, that's my safe. Okay, she's going to lock it as a key, and she's going to hang on to the key, but she's going to send the safe over to Bob. Okay, so now Bob holds the safe. He knows that the bit is inside, right? But he can't look at the bit. Okay, and then later, sometime later, once Alice is ready, she's going to send the key over to Bob, who then can open the safe, right, and find out the bit. Okay, so this is what we want to do. This turns out to be very fundamental for cryptography. The kind of situation you might imagine it coming up is something like, we're doing like a blind auction, for instance, like you put your bid inside the box and other people aren't supposed to be able to see what your bid is until it's revealed. Things like this. But okay, so for us, this is just what we want to achieve, but we don't want to achieve this using some physical object like a safe. I just want to, send you classical or quantum information and have us be able to achieve this functionality. Okay. And we want it to be secure in the sense that it's not just that you don't have a good enough hammer to break open the safe. We want it to be like against the laws of physics to break this. Okay. Okay, so a bit more formally, that's kind of the picture version. But formally, what do we want to achieve here? We want two properties. So the protocol is going to look like, step one, Alice is going to prepare some state, okay, which is indexed by this bit B, and it has three subsystems. We'll call them A, B1, and B2. Okay, so she's supposed to prepare, one of two different states corresponding to which bit she wants to commit to. B is 0 or 1. Okay. And then, let's call that prep, right? And then there's like two steps. So the first step is Alice commits, which involves her sending, let's say B1. Okay, so that's the analog of here, Alice has put the bit inside the safe. That's like she prepares the state. And then she takes the safe and she sends it to Bob. At that point, she's committed to the bit. And here, that's like she sends B1. Okay. And then there's the second step, which is the reveal phase, where she sends B2. Okay. And what we want is two properties here. So we want that the protocol should be hiding, okay, so which means that the density matrix on B1 should be the same regardless of the value of the bit. Okay, so that's like saying Bob can't look inside the safe before I've revealed, right? What Bob has in the commit phase is independent of what Alice is committed to. Okay, and then we want a second property.
Is that supposed to be a B1 on the right?
Oh, yeah. Yeah, both B1. Okay, so then there's a second property that it should be binding, which means that Alice can't change the bit she's committed to. Can't change B. Can't change B after the commit phase. So in other words, once she sends B1, if she initially prepared the state B equals 0, she can't then send something, she can't do something on A, B2, such that when she reveals B2, now Bob reads B equals 1. Right? She can't change what Bob's going to read after that initial commitment. Okay. Okay, so it's a little bit elaborate. Hopefully that makes sense. Do you have intuitions? Is this possible to achieve in quantum mechanics? Can we get both of these properties true at the same time for some maybe fancy choice of quantum states?
Yes.
I have a yes. Someone want to be bold and come down on the no side. Okay, good. Okay, so it was actually an open question in the literature for a while, and there's wrong papers claiming yes. But eventually it was realized that the answer is no. Actually, quantum mechanics forbids you from doing this, and basically the reason is just this theorem. It's not obvious when you first look at the problem, but this theorem tells you this is impossible. So why is that? Where do I want to go? I want to go here. Okay, so well, on the no side, do you have an argument for no, or are you just saying no?
I'm just saying no.
All right, fair enough. Okay, so why is this impossible? Well, basically, the logic is that we can show that if it's hiding, then it's not binding. Okay, so these properties are in tension with one another. And how do we show that? Well, hiding, recall, amounts to this statement that psi 0 on B1 should be the same as psi 1 on B1, right? This state that Alice was supposed to prepare initially, the pure state, psi 0, A, B1, B2, that's a purification of this psi on B1, right? Similarly, this other state, where Alice is supposed to have committed to 1, this is also a purification, right? But these are the same density matrix, right? So let's call that sigma on B1. So these states, right, on A, B1, B2, psi 0 and psi 1, are both purifications of the same density matrix, sigma B1. So according to our theorem, there has to exist some, in this case, unitary, because these are both in the same Hilbert space. So there has to exist some unitary on A, B2, such that the unitary A, B2, psi 0, A, B1, B2 has to equal psi 1, A, B1, B2. Right? These are purifications of the same state, so they have to be related by a unitary acting on the purifying systems, which here are A and B1. Right? But then, you know, we're dead in the water, right? Because what we wanted to be binding was exactly that this unitary should not exist. That Alice can't, after she sends B1, change the psi 0 state into the psi 1 state. Right? But yeah, so we have a contradiction. Okay? Questions about bit commitment? Yeah.
Can you understand it from sort of like entanglement perspective? Like if subsystem, like essentially this not binding seems like she cannot steer the subsystem B1 in some direction, so that means that not binding means that there shouldn't be an entanglement between subsystem A, B2, and B1. I'm not sure if it's the right intuition, but
Yeah, I don't know. I don't really see a way to understand it that way.
okay.
Yeah. Other questions? Okay. So we'll keep going. Okay, so I now want to do a quick recap of quantum channels and generalized measurements. We're going to need them for the next thing I want to do, so I just want to make sure we're on the same footing. So let's start with channels. Okay, so a general quantum channel is like an evolution of a density matrix that has the following form. So rho goes to what we'll call n of rho. And we can always express this in two different ways. So one way is the following. Okay, so the evolution consists of, I take some ancilla system, B, right? I apply a unitary to the thing I'm interested in, row A, along with B, and then I trace out B again. So I'm evolving just the A system, but by interacting with some larger space. Okay? And then there's always another way to write this, which is sort of intrinsic to the A Hilbert space, like doesn't involve bringing in this B system, which is the Krauss form. So that looks like this. There's a set of linear operators, EK. Okay. And this set of linear operators has to have the property that EK dagger EK summed over K should be the identity. Okay. And then there's a theorem, which I'm skipping, but I think you've covered, that says that any evolution in this form, right, I add this system, I do a unitary, I trace out the system, or any evolution in this form, they are equivalent. So, you know, anything of this form, I can find some set of operators EK that gives me the same evolution. And for any set of operators EK satisfying this thing, I can find some unitary and think about it this way. Okay. Is that a familiar statement? Yeah. Okay. Good. Actually, okay, I'm going to be very inefficient in my boards and go back here. Okay, and then there's measurements, right? So far we've discussed projective measurements, but there are more general measurements that you can do quantumly, and these have a similar spirit, right? So they come from adding in some extra system, evolving with the extra system under some unitary, and then measuring, you know, projectively on that larger system. And then there's some like intrinsic description of that to the Hilbert space we're interested in. So I want to quickly just review the formalism there and the conditions. So I'm just going to summarize with the table. So we have already projective measurements. These are defined by a set of projectors. Right. There's some sort of completeness or normalization sort of condition. Okay, which in this case is that if I sum over the projectors, I get the identity. You can think of this as coming from the fact that probabilities need to sum to 1, right? It imposes some condition here. Actually, need to be a bit more compact, sorry. Okay. And then the probabilities are given by tracing pi I with the state, with rho. And then there's some rule for the post-measurement state, which in this case will be like pi I rho pi I normalized by this probability pi. Okay. So some rho I. Okay, right. But then we have these generalized quantum measurements. And here we just have some set of operators, Mj. They just have to be linear operators. we have a completeness condition. To calculate the probabilities, I have MJ dagger, MJ row. And then the post-measurement state looks like MJ row, MJ dagger over PJ. Okay. And then finally,
Sorry, these don't need to be positive, just linear.
yeah, they're just linear. Yeah, yeah.
I remember during our quantum theory class, we learned that POVM will tell you how the state updates.
Yeah.
Can you comment on the state update rule?
Oh. So generalized measurements are not the same as POVM.
Okay.
So maybe, I don't know, maybe you didn't cover this. But so for POVM, yeah, it doesn't tell you. That's right. And then this generalized measurement thing, it's basically MJ dagger MJ that is the POVM element. So yeah, here.
Is it like a CPT-NI then?
Sorry?
Is it a CPT-NI where each MI row, MI dagger is like a Krauss form of a like self-normalized quantum channel?
Yes, I think that's true. Okay, so maybe I should review this. I'm not actually going to use this today, but maybe I should come back and review this form of measurement because it sounds like you guys haven't covered it.
Right, I think when we covered it, we called it a, or this could be
Yeah.
wrong, but we covered quantum instruments and
It's a special case of a quantum instrument, yeah.
it's a quantum instrument.
Yeah.
Thanks.
Yeah. Yeah, but okay, so POVM, here the elements are positive, so that's probably what you were thinking of. And they have to sum to the identity. And then Pj is trace lambda j rho. So a POVM is basically just like, I start with one of these generalized measurements, and I only keep the data that I need to get the measurement probabilities, and not the data that I need to get the post-measurement state, right? So we see that the probabilities only depend on MJ dagger MJ, right? And so I just start keeping track of those, and I call them lambda j, right? And then, you know, if I'm thinking that, oh, M dagger M, that's like a lambda, this condition becomes this condition. And yeah, basically because these lambdas are like M dagger M's, that's why they're positive, because an M dagger M is always a positive operator. Yeah. In practice, I'm actually going to use POVMs. Yeah. Okay. Other questions about measurements? No. Good. Okay, so now I need to do a bit of a just math aside. So this is going to come up, you know, later this lecture or next lecture, depending on how far I get. Just about, you know, facts about positive operators. So, so if I have a Hermitian matrix, Hermitian operator, we have this notion of this being positive, right? And this just means, you know, all the eigenvalues of A are non-negative. Okay. And then we can write things like this operator is greater than or equal to that operator, right? And the way to interpret that is just as saying that A minus B is a positive operator, right? Okay, some little facts about this idea. So if I have, fact number one, if I have an operator that is smaller than the identity, less than or equal to the identity, some Hermitian operator, then one thing that means is that the eigenvalues of A are smaller than 1, right? And why is that true? Well, this, I should interpret this as saying I minus A is a positive operator. Let's write A in its eigenbasis, right? And then let me write the identity also in A's eigenbasis, right? All the eigenvalues of this thing are positive, but the eigenvalues of this thing, like this matrix, is just 1 minus AI II. These are the eigenvalues. So I get that the AIs have to be smaller than 1 for each I. Okay. Okay, and then sort of fact number, actually, let me try and do it here. Fact number 2, if I have a matrix that's positive and smaller than the identity, then trace, I get the following trace inequality. So trace AB will be smaller than the trace of B. Okay, so why is that true? Let's just try and compute it, or compute trace of AB. I'm going to write A in its eigenbasis. So that these states label the A eigenbasis. Right, using cyclicity. And then I also know that the trace of B is just, all right, okay, let me write this. Okay, so this is clearly less than the sum over I, B, I, since all the AIs are smaller than 1 and larger than 0, right? And that follows from fact number 1, right? And this assumption. But then this sum is just the trace of B, right? When I compute the trace, I can use any basis. I could, in particular, use the eigenbasis of A. So that's trace B. Okay, and this was true for any B, right? I didn't use that B was Hermitian or positive or whatever. It was just true. But, yep.
In this proof, we used that AI is less than or equal than 1, but we never used
Yep.
the other side of the inequality, that A is greater.
Oh, no, I did implicitly, because if this was some large negative number, I mean, these can be negative as well. So like this inequality wouldn't follow. This follows because this was true because AI was between 0 and 1.
Oh, okay.
Yeah, yeah.
So suppose that trace of B is like minus 1. Wouldn't trace of AB be something like minus 0.5, perhaps?
Trace of B.
Like basically, like suppose trace of B is like negative.
Oh, sorry. Maybe I did need that B was positive, right? Right. You're saying trace of B is negative.
Like
Trace of A smaller.
If you have a single AI that is like if they're all 0.5, then it's going to be half the trace of B.
Yeah.
And if it's negative, then it's going to be bigger.
Right.
suppose A and B are 1x1 matrices, and then
Yeah. Okay. So I forgot some condition on B. Sorry.
So maybe you don't need A to be positive, but just B to be positive. Because then if A is negative, it's just going to make it smaller.
A is negative. Sorry, it's hard for me to figure this out on the spot. Okay, I think I should just come back to it. Forget it for now. I'll do it next lecture and figure it out properly. That's weird. What did I do? Okay, anyhow, yeah, I don't want to waste our time. Sorry. Okay. So let me just plow ahead with lecture 4. So we've, kind of encapsulated lecture 3, which had to do with channels and measurements. But you guys knew that stuff, so I've done that very quickly. Okay, so lecture 4 is about quantifying how different quantum states are. Okay, or how similar they are. And this is a really central subject for quantum information theory. Okay, you often want to know how similar different states are. So, for example, you're trying to build your quantum computer, and the computer is going to have some sort of noise in it. You want to know, is this like a large amount of noise or a small amount of noise? Does it kill me or is it fine? And the way that you would quantify that is like, are my states close to what they're supposed to be or not? Right. Okay, so we need to do that. We're going to have 2 different notions of how similar or different states are. The first one is something called the trace distance. And the second one is the fidelity. Okay. And we're going to get a start on the trace distance today, and we'll talk about fidelity next lecture. Okay, so the starting point for the trace distance is the following sort of very reasonable idea. Okay, so we're going to say, suppose we have the following scenario. You're given one of 2 states, rho 0 or rho 1. You're given each of them with probability half, and at random, like you're not told which one. So I just give you some quantum system. You don't know what state it's in. You do have a promise that it's either in the state rho 0 or rho 1. Okay. You want to figure out which one is which. The way that you're going to do that is you're going to make some sort of measurement, right? And then you're going to, based on your measurement outcome, guess that it's rho 0 or guess that it's rho 1, right? So to do this, you only need a measurement that has 2 possible measurement outcomes, right? So we can always think of this as some 2 outcome POVM, lambda 0 and lambda 1. And then, without loss of generality, we can say that, okay, if I get outcome lambda 0, I'm going to guess that it was rho 0. And if I get outcome lambda 1, I'm going to guess that it was rho 1. Right. Okay. And the way that we're going to try and quantify how similar or different states are is we're going to say that states are very similar if it's very hard to tell them apart, right? If your probability of getting this correct is basically 1/2, then these states are basically the same thing. So I claim that there is a simple formula for this thing. And in particular, I claim that max lambda 0 trace lambda 0 minus rho 1. So this maximization thing is just equal to half of the trace rho 0 minus rho 1. Or this is an absolute value. Okay. Okay, so I don't have probably enough time to prove it, but let me start on the proof. Okay, so first observation, rho 0 minus rho 1. This is some new operator. It's still Hermitian, right? Rho 0 and rho 1 are, so this is Hermitian. So I can diagonalize this. It's going to look like this. Now, I don't know that this thing's positive anymore. So these lambda i's are just real numbers. They could be negative, right? So lambda i's are real valued. I'm going to make some definitions. That'll be convenient. So I'm going to define P. This is basically the positive part of rho 0 minus rho 1. Okay, so I pick out all the non-negative eigenvalues, and I just keep those. Right? I also define a projector onto the positive eigenvalues. So that's sort of the same thing almost, but without the lambda i's. Right? And then similarly, I'll define Q as lambda I, the negative part. Now I put an absolute value on the lambda. Okay. And I define a projector onto the negative eigenvalues. Okay. One observation. You can note that rho 0 minus rho 1 is equal to P minus Q. Right? Which just follows from the definition. So this, I've just split the eigenvalues into two sets. I took an absolute value sign here where these were negative, so that this thing is some positive operator, but then this minus sign is going to restore the sign to the lambda i's, and these will be the same. Yeah. Okay. Okay, so the idea here is that actually the optimal distinguishing measurement to make in this setting is to measure the set of projectors pi p and pi q. Okay. Or, in other words, the optimizing choice of lambda 0 in this expression is exactly pi p. Okay. So this is the optimal, the maximizing. That's the maximizing one. Okay, and then if we actually go and compute what the maximum is, so I'm saying, pi p is the maximizing argument here, but then if I go and compute this quantity with pi p inserted, it's going to come out to be this, this expression. Okay. Okay, so let me do that. Where do I want to start? I want to start with okay, so let's first of all show an upper bound on this maximization. So to do that, okay, let's say upper bound. Max lambda 0. Trace lambda 0. Okay, so this is also equal to the trace. Actually, okay, let me just say this is for an arbitrary choice of lambda 0, and then I want to upper bound it. Yeah. So I can replace row 0 minus row 1 with p minus q, because those are equal. I can think of this as two terms. So this is like trace lambda 0 p minus trace lambda 0 q. These are both positive operators. So this trace is positive. So this is always less than if I just keep the first term, lambda 0 p. And then I need to use this math fact I was confused about before. And I think this maybe clarifies what the right assumption to put in there, which is that I want to say that this is less than trace of p, right? So this was like my trace AB, and then this is like trace of B. And so, yeah, here actually B is a positive operator. So presumably that's the assumption I was missing when I got confused there. But I need to rethink that proof now and see where that was actually coming in. But okay, so if you buy that for a second, then we have this upper bound that this thing is always less than the trace of P. Yeah. Okay, good. And then, okay, and then I want to say that I can actually achieve this upper bound by making the choice that pi 0 or lambda 0 is equal to pi p. Okay, so to show that, I just need to compute this, right? And again, I'll replace row 0 minus row 1 with p minus q. Pi p, this is a projector onto the support of p, right? So it kills q. So this is trace pi pp. But, okay, this is also, yeah, the projector onto the support of p. So pi p into p is just p again. So this is the trace of p. So that's good. So that's saying that this thing is always less than the trace of p, which in particular is equal to this. So just to summarize, we have that the trace of lambda 0, row 0 minus row 1, maximized over lambda 0 is just equal to the trace of trace of pi p row 0 minus row 1. Okay, and I think I should leave it there. But the remaining step, right, is that, so we've like found what the maximum is, and we kind of have this explicit expression for it, and then we just kind of have to massage this to see that it's actually equal to this expression in terms of the density matrices, right? So that's the remaining step, and I'll do that next time.